Hello everyone, thank you for attending our presentation. My name is Nimit Kalra, and this work is in collaboration with Brady Joe and Philip Krahenbuhl. I'll be speaking about our simple framework for domain adaptation called task distillation. Real-world autonomous driving is difficult. Agents must make consequential decisions in potentially unseen environments. This is further complicated by the difficulty of collecting the large amounts of real-world data needed to learn effective policies. For example, repeatedly crashing a car into a tree is simply too expensive. On the other hand, simulators safely and effortlessly produce massive amounts of labeled data at virtually no cost. Unfortunately, models born and raised purely in simulation often fail to perform well in the real world. We can clearly see that these simulated environments vary dramatically from real-world scenes and all of their intricacies. How can we reduce the domain gap between these domains so as to successfully transfer agents from one to another? We begin with the observation that large visual recognition datasets exist in almost any interesting domain. How can we leverage these widely available vision datasets to transfer representations from environments wherein collecting demonstrations is easy, such as a simulation, to environments wherein collecting data is difficult, such as the real world? Let's formalize this. Given a model that performs some task in a source domain, our goal is to produce an adapted model that performs the same task in a target domain. We assume we have no output labels in the target domain, but do have access to visual recognition labels, such as semantic segmentation in both domains. Let's start by looking at a simple baseline, ignoring the issue of domain shift altogether, and simply deploying a model trained in the source domain onto the target domain. When the domain gap is large, this direct baseline will fail, as the source model has not seen images from the target domain's raw input image distribution. What if we try to remedy this failure by aligning the raw input image distributions of the source and target domains? Pulling from a promising body of recent works that perform image-to-image translation and style transfer between domains, we attempt to translate raw target domain images into the style of the source domain. At test time, we applied the image translation model to the target input image to generate a source-like image, which is then directly fed into the source model. Unfortunately, when a large domain gap exists, as is often the case between simulated and real domains, these pixel-level adaptation methods suffer. They produce poor translations, which contain artifacts of the target domain, and fail to consistently enforce semantic relationships. As models trained on raw image inputs tend to be unforgiving to such visual artifacts, unsupervised domain adaptation techniques suffer both from the translation errors and, like with the direct baseline, the visual domain shift that exists. Raw perception is very rich, however domain adaptation at the raw image level is clunky and error-prone. Recognition labels, however, are compact and abstract representations of the world. As a result, the gap between label spaces is small, even for domains with a large visual domain shift, and these representations tend to generalize. Rather than perform image-to-image translation between raw images, what if we work with these abstract representations instead? First, we train a proxy model that acts on some abstract intermediate representation in the source domain, generally a visual recognition task such as semantic segmentation. Next, a vision model maps the raw image to this intermediate representation in the target domain. Finally, we can stack this vision model with the source proxy model at test time. Since the domain gap between label spaces is small, this representation will generalize. However, solving recognition turns out to be quite difficult. Current recognition systems mislabel objects, detect an object where there is none, or worse, fail to recognize important objects altogether. These errors compound to downstream tasks. We take a different approach. Again, although raw image inputs may be drastically different across domains, their recognition labels tend to be quite similar. We use a small domain gap between these labels to aid in transfer. First, given a source image model, we use model distillation to produce a proxy model that operates on recognition labels. Next, we use the same proxy model to produce proxy labels in the target domain. One major benefit of the proxy model is that it operates on ground truth proxy labels. if the proxy labels are carefully designed to encode relevant information for the downstream task, this makes the transfer trivial. Finally, we perform model distillation again to obtain an adapted image model in the target domain. This target model has been trained using only images from the target domain, so there is no reliance on raw image input generalization, as there is with the direct baseline. Moreover, task distillation does not suffer from the compounding errors due to test time image translation or recognition prediction failures, as do unsupervised domain adaptation and modular pipeline approaches. Instead, our method's transfer success hinges on the domain gap in the proxy label space, which is generally quite small due to the nature of recognition tasks. Moreover, this gap is easy to close since these proxy tasks can be hand designed or altered as needed. In summary, ignoring the issue of domain shift is ill-advised when the domain gap is large. Unsupervised domain adaptation techniques such as cicada produce poor image translations that maintain a large domain gap with the source domain's input distribution. Finally, modular pipelines must infer recognition at deploy time and query a proxy model with predicted labels, thereby incurring the cost of an imperfect recognition system and leading to compounding errors. Task distillation instead queries the proxy model at train time with ground truth proxy labels. We perform controlled experiments to determine the effectiveness of each method in transferring visual navigation policies between simulators with very large visual domain gaps. Policies are transferred from SuperTux Kart, a simple racing game, and Vizdoom, an old-school arcade game, to Carla, a photorealistic driving simulator. In SuperTux Kart, we train an agent via reinforcement learning to navigate a winding racetrack. In Carla, we evaluate the transferred agent's ability to perform lane following with no traffic participants. Similarly, we train an agent in Vizdoom to navigate a maze while avoiding poison obstacles, and transfer to perform vehicle avoidance in Carla with moving traffic participants. For each transferred policy, we evaluate how far the agent travels until a driving infraction or collision in an unseen test town in Carla. We start out with a simple direct baseline. If the visual domain gap is small, then no domain adaptation is necessary. However, SuperTux Kart and Carla have an enormous domain gap, and transfer is extremely weak. Vizdoom and Carla have a similarly large domain gap, and the transferred agent fails. Pixel-level domain adaptation methods such as cicada may be able to recover the style of the SuperTux Kart domain, however their image translations are poor. Moreover, they sustain the large domain gap between the raw image input distributions of the source and target domains. In turn, the source model fails to output reasonable actions. Our image-to-image translation models from Vizdoom to Carla are significantly better, however the entire pipeline still performs quite poorly. The predicted semantic segmentation modality is accurate. A modular pipeline works quite well in transferring from SuperTux Kart as well as from Vizdoom. Since our task distillation approach does not rely on deploy time vision inference, it does not suffer from compounding errors due to vision failures or poor image translation, as do modular pipeline approaches and unsupervised domain adaptation techniques. As shown, our method greatly outperforms the modular paradigm, nearly doubling the mean distance traveled until infraction. Our policy transfer experiments concern a very specific domain adaptation application. However, task distillation is not limited to transferring sequential decision-making policies between domains. We can apply our framework to transfer general computer vision tasks from simulated to real-world datasets. We use the low-level visual signal of depth estimation as a proxy task to transfer semantic segmentation from the Cynthia SF source domain to the Carla and Cityscape target domains. Following the setup of Ramirez et al., we see that our far simpler task distillation framework outperforms their ATDT framework in mean intersection over union. All our code and data is publicly available, and we hope to see you at our poster session where we're happy to answer any questions and further discuss. Thank you.